So I'm starting with, so who here doesn't know any physics? I hope there are some people. Ah, good. I'm going, before starting with more formal treatment, I'm going to give a little bit of a naive account about what is the difference between what computer scientists call bits and qubits. Like, a bit is nothing else than just a Boolean variable. And a qubit is the same equivalent, is the equivalent of that in two-dimensional Hilbert space. So a bit, to put it in slogans, it admits only two values, 0 and 1. It admits arbitrary transformations, meaning you can do whatever, any function you can apply to it, and there's no problem. It sounds a bit silly if I put it like that, but it's just to put a contrast. And it's freely readable. Again, what does this mean, freely readable from a Boolean variable? Well, the reason I put it like that is because, in contrast, a qubit can take a sphere of values, so mathematically it's basically in the projective spans spanned by 2 points on the sphere. So if you've got a sphere of values, so this is a sphere, then you've got a 0 here, a 1 there, which is a basis arising from the underlying complex Hilbert space, and then if you go to the projective space over it, you get a sphere. So that's how the sphere of values for a qubit arises, and in a way it's spanned by 2 points, 0 and 1, like in the projective sense.
Have you deliberately drawn those antipodal loads?
Yes, that's deliberate, yeah. So it's a little bit here. It only admits special transformations which preserve the angles, and on the sphere, this means the opposites, because opposite on the sphere means orthogonal in Hilbert space. So you can easily see this in two-dimensional Hilbert space. So we're talking about, so you start with, so you got 0 here, a 1 there. You start rotating, you're discovering new points. But once you're here, you're in the same ray. So you close up. So whatever is 90 degrees here, whatever is 90 degrees here, comes 180 degrees there.
Sorry, I think it might be helpful to say that the sphere is the CP1.
Yeah.
It's the Riemann.
Yes. Yeah, please interrupt me at any point. So, of course. Yeah. So the transformations on the sphere are reversible, so you can't just do anything on it. You always have to preserve these opposites. It's by Wigner's theorem, it's actually enough to preserve the opposite to know that you then preserve all the angles. So now, but this is the big deal about. This is where all the sort of trouble comes in. It admits reading. Like first, I mentioned that for the quantum system, for the classical system, these values are readable. For the quantum system, they are only readable through so-called quantum measurements. The quantum measurement is defined by 2 points, which are called plus and minus, which are again opposites. So maybe here is plus, and there is minus. So they're again opposites. So you've got a measurement defined by some of the. And what happens is that what the measurement will tell you is a number, either plus or minus. It will tell you either plus or minus, corresponding to, it's saying that this is your outcome or this is your outcome. Now you have to realize that initially your system might be here. Initially it might have been here. But the measurement can only tell you plus or minus. And basically what it does then is, if it tells you plus, it will change this one to the plus value. If it tells you minus, it will change this one to the minus value, and this happens in a non-deterministic fashion. So to put it crude, it doesn't really tell us the state of the system we are measuring, it basically destroys it. So this, just to put it really crude, what a quantum measurement does for you is destroying your system or your state and putting it in a new state, which you basically choose by choosing which measurement you do. It's sort of a very crude way, but it's just to put it that typically people use the name observable for these things, but there is nothing observing about all these things. You don't observe anything. You're basically changing something about a system. It's an act of dynamics. It's an act of dynamics. And this is the whole lessons about quantum mechanics. And of a lot of the phenomena I'm going to talk about are basically consequences of this fact that you can't just observe what the state of a quantum system is. You can only do something to it which alters it. Now, fortunately, it's not all that random. It seems quite random, but it's not all that random. So let's look at a more concrete. I'm going to go through a more formal treatment of everything later. It's just like now to put the essential concepts right. So that's what I just said. So suppose we've got a system in a state psi. We do a measurement plus or minus. That's the measurement we do. So one out of two things is going to happen. And I represent this by partial constant maps, I would say. So either this state is going to change to plus, or this state is going to change to minus. And it does it with certain probability, namely, it looks at the angles here, and if this one is close there, then the probability to go there is higher than to go down. If it's closer here, then the probability to go here is higher. And effectively, if this one is equal to that, then with certainty you will obtain this outcome. So if this system happens to be in plus, then you will see plus. If it happens to be in minus, then you will see minus. If it's very close, then you're very likely to see minus. If it's in the middle, then it's 50-50. So this is the probabilistic nature of quantum mechanics. So we're basically talking about two partial maps. So the P plus map will send anything to plus except for minus. It never changes the minus to plus. And the P minus map will change everything to minus except for the plus. And in the middle, it's sort of a continuous transition from highly likely to very unlikely. And now, so what I'm talking about here is, this is not the usual way. Like most textbook presentations make you feel as if quantum mechanics is as close as possible to observation. It's the best you can do. And the point I want to make here is that actually you can use this measurement as a dynamic resource, which you can use to do weird stuff which people were never able to do before. And I'll describe a couple of phenomena now of what you basically can do. But let me first vaguely formalize this, just to give at least you some mathematical handle on the thing. And we're going to do a better treatment later. Take this keys away because I just talking. So, the state of a qubit, as I indicated, is described by a pair of complex numbers up to a non-zero complex multiple. So we're really talking about arrays, one-dimensional subspaces, in the two-dimensional complex Hilbert space. That's where you describe them. So there are two numbers, and basically, if you have a complex number as a multiple, then you're talking about a non-zero complex number as a multiple, then we're talking about the same state. And the typical notation, which I was saying, is people tend to use this as a notation for a base vector like 0 and 1. So this is a choice of base, like I indicated here. And then you got your complex coefficients. And then these measurements, naively, are just matrices, so we're doing linear algebra. For example, this would be the one which projects on 0. This would be the one which projects on 1. So if I get any input vector, I apply the first projector to it, I get this out. If I take this as input vector, I apply this projector, I get this one out. So basically, you see there's not a lot left of your initial states, it's Z1, Z2. There's not a lot left of that. Basically, there's nothing left anymore. Except for when this would have been 1 and this would have been 0, then we recover it. If this would have been 0 and this would have been 1, then we recover it. But otherwise, all that data is basically destroyed. So, this is all very naive, of course, but just to, I think the main concept in quantum physics is which I think we need to understand better, is basically quantum measurement. Most philosophers agree on that, and there's like about thousands and thousands of papers written on what is called the quantum measurement problem, and as far as I know, none of them is satisfactory anyway. I think people agree on that. We've as the result that I think about in 1970, like 1980, something like that, people just decided not to fund foundations of physics anymore, because people just kept on talking about the measurement problem and nothing was coming out of that. So,
I guess I would say that I think the decoherence program is very good. The decoherence program.
well, there's, yeah, but it hasn't been accepted at all, so...
I disagree for some reasons, and this is...
Well, as long, there's still a lot of people, I'm sure, like, I would say that still like 20–30% of physicists would never accept any approach which is not a hidden variable approach, for example. These programs are still open, for example. So, it's hard to say anything about it. So, now what can we do with these things? And so, I'm going to discuss some more recent experiments which actually have been done in the lab. Because we're talking not about theoretical things here, we're talking about actual phenomena which people have realized in the lab. So the first one I'll talk about is quantum teleportation, which was done in 1997. The big surprise actually that was only discovered in 1993. We're going to prove this later. It's a totally trivial thing, completely trivial thing. It's amazing that nobody ever discovered that. Like the quantum mechanical formalism was like from 1932. A little bit earlier, but like the von Neumann formalism was published in 1932 in his book. And this is such a trivial phenomenon, and it took basically 60 years to be discovered. That you can actually, that quantum physics offers you this capability to do things. And well, you see, this is typically what linear optics realization. People in optics are really good in doing this sort of quantum experiments. So what is the phenomenon? I call it a phenomenon. Some people would call this a protocol. I think it's a phenomenon. It's a physical phenomenon which you can make happen. So this is basically the setup. This is like that. So we'll discuss this formally. I just now want to show the phenomenon which we can basically do using quantum mechanics. So the idea is the following. You've got three systems. You've got three systems which are represented by lines here. 1, 2, 3. So time goes up in my pictures. So one system is in a certain state. This is system 1, say, and then you've got system 2 and system 3. So you've got two things, one thing here. But I represent the state in which they are by this weird spread out triangle. That's because they are in some fancy state which is typical quantum mechanical. Don't care about this at the moment, what this fancy state is. The idea just is you've got a state here, you've got a state there, but they are in some fancy state. But one is, for example, just to say, people have done this across the Lake of Geneva. So this is one side of the Lake of Geneva, this is the other side of the Lake of Geneva. But they are in a special state. I'll explain later what this is. But there is one thing sitting there, and there is one thing sitting there. Then this person...
Just to anticipate you, this is entanglement.
This is entanglement, of course. This is entanglement, of course.
So you're actually taking the tensor product.
Yes. I'm just giving what this is basically the realization an experimenter is doing. Like you got Chizin sitting at one side of the Lake of Geneva and one of his assistants at the other side. So this is Chizin doing these things here. This is the other guy doing these things here. Now there is of course a fancy connection between these two things, which is called entanglement, and which is something they worked on in the past. But they're both sitting there with their quantum system. So then, here, Chizin does a measurement. He does a quantum measurement, like I explained before. When you do quantum measurement, you have a number of possible outcomes which can happen. One of these projectors which destroys the state and changes it in something else. So this is what he's doing here. This is non-deterministic. You never know which one of these projectors is going to happen. Typically, if these are 2 qubits, then this will have 4 outcomes because we're working in 4-dimensional space, 2 times 2. He sends the outcome to the other guy, he calls him, and he gives him a number between 1 and 4. There's 4 possible outcomes. And then this guy does a certain operation here. And as a result of this protocol, whatever quantum state was here, which is a point on the sphere, will be there. So the sort of magic of the thing is that when they called on the phone, they only mentioned the number between 1 and 4. So there was discrete data transmitted, while ultimately the state of the system, which was here, will be there. So continuous data sort of went from one side of the lake to the other side of the lake. while on the phone they only talked about a number between 1 and 4. So that's the phenomenon. That's a phenomenon you can do with quantum mechanics. We'll explain how it works, but this is a phenomenon. Yeah, it's clear what this is? This is phenomenon. You can do that. People have done it in, well, in 97 it was just small in the lab, but now they're doing it over amazing distances.
But let's say that, of course, one-hand data is classical bits on your line.
Yes, sure.
It's also important to understand.
Sure. So this is quantum. This is quantum data, and typically you don't know what the state is. This quantum state. Typically you don't know what it is because you can't just look at it and know what it is. So it's typically unknown quantum data, but you transmit it.
Okay, let me make sure I understand. Now, a critical point here is that Mr. Yu does not measure the spin of the thing that's going through.
Sure. This is something you nourish and don't want to destroy. You don't want to measure it because then you destroy it. And if you would measure it, then it's trivial. You measure it and you tell your guy the other side what you measure, then he just reconstructs it. The thing is, this is something you cherish and you want to keep the way it is. But you do want to get it to the other side of the leg.
But how you identify, how you compare
the secret across the leg.
Yes.
Yeah.
It's a for the observer unaccessible secret. You'll never get to know it. But you can sort of exchange it. You can. It's a continuous data secret. It's a point on a sphere. But I can get it from one side of the leg to the other just by communicating 4 numbers.
But,
one number out of 4.
But if you didn't measure it, how do you know it's the same?
If I measure it, you destroy it.
Yeah, but if you don't, how you know it's the same? Or the both
Well,
sides?
you can do statistics. You test. You do it 1,000 times. You do it 1,000 times, and then there is a branch called tomography. It means if you do enough if you got enough copies of the same thing, and you measure it enough, then you sort of know what it is. But you need like you need big statistical data for that. So that's how they check it, of course. They do it like a lot of times.
It's of course also very important to understand. But this is almost talking about an experiment, and you can check if you have the same state. At least statistically, you can check this when you have many copies, and you experiment very often. And of course, the idea is you must do this and compare this with the predictions by quantum theory, which are very strange actually. But it turns out that the predictions of quantum theory actually are validated by experiment. That's interesting. Of course, there are always these two sides to things. That's very important. And a number of things I'll say later on in my talk.
So the thing you have here is the thing. I think Andreas is going to talk about Bell inequalities, and Bell inequalities they aren't as pretty as an experiment as this one. But what they tell you is that there is no other way this can have happened. You couldn't find any fancy statistical theory underlying all this which would explain this in some other way. That's what Bell inequalities are about. But there is this historical thing that until say the 1980s, people were sort of looking at quantum mechanics as something which was wrong and one way should have been fixed, and probably these Bell inequalities will never be violated. In 1981, they actually happened to be violated, so we know that these things do happen. You know that. For sure. There's still people writing papers about it. It's all like a hoax and things like that. They're still busy doing that. Like this sort of phenomena, like they're just done. If you look at the experiments, they're quite simple. The teleportation one is really simple. This is just plain linear optics. This is like with light on benches. It's very simple. So it's not very complicated machinery. It's not like nuclear reactors or the stuff they are doing in CERN. It's very small. It's very small stuff. Now here's another one which I wanted to mention because it's very recent. When you say this is hot stuff, this was realized in 2007. Now I'm thinking. So teleportation, this was Zeilinger who did this. Zeilinger in Austria. I think this one is Zag in Switzerland, in Geneva. It's a variation on the same theme, but they are just funny phenomena. So while teleportation was about sending continuous data with only a finite number of bits, this is actually about entangling things without touching. Now, what does entangling mean? Well, obviously in the teleportation picture, this very special state which I connect. You just look at the topology of it. Just look at the topology of these things. I know that a lot of you are used with wire diagrams and these sort of categorical things, so I think you can already see a little cup there sitting. So basically, you have to think of this entangled state as a channel to which something can flow. Almost like a quantum channel. Although these are two systems, the special feature of quantum mechanics is if you've got two systems together, you actually shouldn't think about them as two systems. You should think of them as a channel, a communication channel. They can speak to each other. They'll always be in contact. And that's the entanglement. And you see there is some topology here. If you start here, I can go through this box, and if I then go through this box, I get there. And that's basically how it happens logically. So you want to think about this as some sort of communications channel. And having established such a channel, typically how people establish such a channel is you take an atom, it decays, and then it emits two things in two directions, and they're sort of connected by certain properties, by preservation laws. And that's actually what causes the channel, that if you do something there, and the other side will be affected by it. That causes the channel. Now, so with this idea of a channel in mind, check out this protocol. It is initially you've got four parties, and A and B share such a channel, and C and D share such a channel. Let me write this down. I've got A and B share a channel. C and D share such a channel. Then you do something on B and C. Which is one of these measurements again. So, I should write C there. And D there. Yeah. So you do something on B and C. Again, there are some local corrections you have to do on C and D. Just ignore them. They are not that important actually here as a teleportation. And the result of the protocol is that ultimately these two, if I do this thing, then these two will get entangled and become a channel. So I've created a channel. We'll prove this later in quantum mechanical formalism. I created a channel between this guy and this guy by acting on this guy and this guy. Again, there is a topology you can see. So initially you see, if you forget about this one, then you see then you got a little connection here, you got a little connection here. Now we put a connection there, and this actually makes this guy connect with this guy. That's basically how it works topologically. And this is very much in the spirit of how the tensor product works. Like people working with tensor categories and like compact closed categories immediately recognize the structure there.
You're using the word protocol. What do you mean by the word protocol?
Oh, do I use it a lot? I try to avoid it and say phenomena. This is what is a protocol? It's like you have some recipe which you follow to do things, and as a consequence of doing these things, there is a result. For example, key exchange would be a protocol, like internet protocols. It means like how your computer deals with incoming signals.
So what does it mean in terms of diagrams? That this is a prescription for an
Right. So that's actually a good question. So if for those who know the mathematical structure of these things and the sort of categorical structure here, then you see that the categorical structure would completely ignore any sort of causal ordering. While the protocol is really what you do. You first do this, then you do this, then you do this. It's like this prescription of doing this, and then knowing what the outcome would be. That's what a protocol is. Like for example, a protocol is when you get money from the bank.
Sure.
So you put your card in, you type in the number, and you know what's going to happen.
It's very operational. You prepare something, some kind of initial state,
just in terms of the diagrams, what's different between, say, a morphism in a category and a protocol or something? But you mean you're interpreting the diagram as an instruction for performing an experiment?
I think mathematically it's imposing a causal order. Like really in category theory terms, it would be interpreting your composition really as after, and your tensor as while. Your tensor becomes while. So you're actually imposing a causal structure on your category.
Or that has to do with the duality structure in the tensor.
Yes, so it's like I would say that's the logic of the thing. While the protocol side is like where you really do things in causal order, and like the duality screw up causal order completely. in this sort of things.
So it's actually, the tensor categories are always tensor star categories. Okay. Do you ever do anything other than bits?
Sure, like, it doesn't really matter, but this is just the standard.
Yeah, because there are some things that are true about that just because you've got a very simple Lie algebra.
Right, sure. But most of the things which I'm showing here don't depend at all on bits, actually. They work for any data. The way I'll prove it will not depend at all on bits or anything of that kind. So what else can we do with quantum phenomena? I'm not going to discuss in detail. There is something really which is called public key exchange. So I was talking about experiments which have been done in the lab. So public key exchange is a way to safely communicate data using one of these quantum channels. And here I'm not going to say experiment has been done, but you can just buy one. I can give you the internet site, and you can even buy one today, and you can just play it at home. So these things are very practicable. They're not that expensive here.
Because it hasn't been done, but you can buy one.
Oh, you go online, you type in your credit card number, and they send you one. I'm serious. And there's two companies actually who compete about this. So it's even part of the competitive market. So you can buy a thing like that. It's not that it's going to be of a lot of use practically. You can play this with bigger children. So you can do this. I don't know how much this costs now, but it's like it's much cheaper than a car. which is not usually the case with physical experiments. So I think one just, if you want to check, so I think ID from Geneva, they are really good. Quantique. I think they sell one. And then there is another one, I think that Magic, they are in the US. I think they sell one too online. So I'm not going to discuss what this is, but again, this exploits this entanglement in a way to share secrets in a much more secure, well actually it's more subtle, but an improvably 100% secure way that you can't crack. So you can buy one of these guys.
So if we buy two, can we exchange public keys with each other? Is it as practical as that?
If you buy one, yes. You can do it. And the only time they really did one, so they have been using this once between, but this of course is a media event, between, I think, how do you call it, the House of Commune, the Maison Communale, in Geneva and one of the main Geneva banks. They really use this for a practical exchange of it. So they did this stuff. I think it was 4 years ago. But it's not in the state that it's going to replace anything people use now. But this is like well-established technology. On the other hand, it's something we were just talking about that before. There is this case for fast algorithms. There are algorithms on a computer which, if you would have a quantum computer, are supposed to be faster than a classical computer. They are not just supposed to be like search algorithms and things, just are faster. There's another one which is about cracking factoring numbers, which is faster than the fastest known classical algorithm. Now this is a very important application because at the moment all the key exchanges which are happening are based on factoring numbers. And typically they're based on the fact that you need like times longer than the existence of the universe to actually execute these factorization things. But if you would have a quantum computer, it would just take you half a day or something. So you could actually crack the codes. But I'm just putting this down as science fiction at the moment because there's no provable, there's no evidence that ever we were going to have one of these. So I think it's still we should sort of glorify these algorithms and tell the people how good and important they are because they bring in research money and jobs in the foundations of physics, and the foundations of physics has been a graveyard of careers for a long time now. So this is like, if they give you something, just take it, whether you believe it or not. So I'm perfectly. So my title here is I'm the Oxford University lecturer in quantum computer science. You see why. Now, so why this sudden new activity? I think a bug became a feature. So, like I said before, until 1980, quantum mechanics was this horrible thing, which people just didn't like, and it was cruel. There was the nice, beautiful theory of relativity, and there was quantum mechanics, and they don't really conceptually fit nicely together. And But then basically in 1982 there was the verification of violation of Bell inequalities, and most sane people then decided, okay, now we will have to live with it and just turn this bug into a feature and see what we can do with it. Like I mentioned, the reason teleportation took so long to discover is just people weren't looking for applications, they were looking for excuses not to use quantum mechanics. They were not looking for applications to do it. And this situation has changed, and although as far as I can see a lot of people now working in the area of quantum computing are just trying to do quantum foundations, but it's just a place to do it these days. Quantum computing is the place to do quantum foundations, because then you can get money. And it's just a matter of just saying, instead of two-level quantum system, to say qubit. And that's the essential difference. So now on the more technical side, so why can we do all these fancy things with quantum mechanics? You've got a gigantically enlarged state space as compared to classical systems. For example, these entangled states are part of an extended state space. You don't have just a state space of one system and the other system. You have something much bigger, which is described by the tensor product. And that's where these entangled states live. On the other hand, measurements are a bad thing, because you've got this extended state space, but you can't read your states of a system anymore. If you want to know what they are, you basically destroy it. So it's sort of a balance. If you want to use this feature of quantum theory, of this new phenomenon it gives you, and you want to study this, and basically you're doing a balancing act between exploiting this enlarged state space and then trying to avoid destruction of your data. So you have to be very clever and very smart to find some advantages in between those two things. And that's why it's so hard. Like, people are looking for these quantum algorithms still, but it's really hard because of this. And some people think there's not anything left to be found there. It's not really nothing. Now, finally, just as a final note for this introduction, I think the most, so there are the things you can do with quantum mechanics, and trying to figure out what you can do is interesting, but probably even more interesting is figuring out what you can't do with it. Because there are some things, like, once you hear these stories about entanglement and you can send continuous data across the Lake of Geneva and things like that, then you start fantasizing and say, oh, probably we can do this too, and probably we can do this too. And then typically the answer is no. So, for example, you would think from the stories I've been telling you that this would enable you to communicate faster than light, or something like that, because all these things are instantaneous. You can't. It's so delicately balanced that that sort of things you can't actually not do. And that's where the big questions, like why? What can we understand this fact that although it gives us these capabilities of doing things which seem to be non-local communication, you really can't send things with it. Because remember, in the teleportation protocol, you do have to pick up the phone and give this number 1 out of 4. If you don't do that, nothing has been transmitted. It's so essential to send this number between 1 and 4, otherwise nothing is transmitted. This is an essential part of the protocol. So those are the big questions. Why is nature so delicately balanced that it just perfectly fits again with relativity? And then even so, people have come up with sort of imaginary states of entanglement, which still don't violate faster than light communication, but which you can't do in quantum mechanics. So there is this delicate level between communicating faster than light and what you can do with quantum mechanics. There's something in between still. And I think this is like where now the actual foundations research should be taking place, and a lot of people are trying to understand what is so special about this phenomenon you can do in quantum mechanics. And I think the way to understand them is really to go to a better formalism, a nice high-level formalism which makes it much easier to reason about things. And I think that's where the role of category theory lies in these things. So, anyway, now go.
Well, can you say more about what a non-local box would be?
So we probably have to talk about it in the next workshop. By John, I wanted to have him now because then we would have had 2 John Barrett. So there is John Barrett is coming from nothing, and there is John Barrett now in Bristol. And John Barrett from Bristol is a non-local box guy. He said he might be coming today, but we'll surely give a talk about that at the next workshop. So it would be like, I can't tell you after, but it's a sort of, it's more than, you can do more, you can violate balance, it's more than entanglement. But So it's called PR boxes sometimes, Popescu-Roerlich boxes. Okay, so things I won't talk about here because it's not that they are not important, but there is a lot of things you can talk about without mentioning them. It's continuous time Schrödinger evolution, which is how a quantum system evolves. I'm not going to mention that. I'm not going to talk about anything continuous after, like continuous observables. Everything will be very discrete. And I also don't care too much about values of observables or spaces where physical quantities lie. I really will focus. This is just basically for the physicists sitting here who say, oh, you didn't talk about that, and you didn't talk about that, you didn't talk about that. But so I don't talk about these things. And so I use pure state here. By pure state, I mean closed system. Now in quantum mechanics, closed system is sort of a delicate concept because everything is sort of open in some way. So otherwise you can't measure it. Now, okay, I think everybody here knows what a Hilbert space is. I've put it on. So is there anybody here who is not completely familiar with the notion of Hilbert space? Finite dimensional Hilbert space? Yeah? I thought so.
Oh, for mathematicians, you should say that physicists like their scalar product of linear the second.
Ah, okay, yeah. So it's linear in this one and it's conjugate linear in this one. So that's basically what it is. Yeah.
Mathematicians usually have the other way around. They get confused.
Yeah, mathematicians here, you mean analysts. Because actually most category theorists prefer the physicist convention.
Yeah.
Because it looks like like a Hom.
Yeah.
If you do it, you want it to be contravariant to the first variable.
Yeah, you're right.
So basically this is just a vector space with an inner product, which values in a complex number. This bit is linear, this bit is anti-linear, conjugate linear. So everybody's happy with that? Hilbert spaces are very easy as long as you stay finite dimensional. If you go infinite dimension, then you can write it around and it becomes a little bit more messy. What?
Hilbert space is always.
Yeah.
Yeah.
So, right. So then, if you've got a Hilbert space, you can define a couple of notions. Like, you've got linear maps, of course, the notion of linear map, and you say that if you've got a linear map which is such that to another linear map this condition is satisfied. So if I put f at one side of the inner product and I plug in f adjoint, I call it adjoint already, I should tag it at the other side, and then you call these two maps adjoint to each other. Call them adjoint. So it's still a bit of a mystery. So I think this is the origin of the categorical notion of adjoint. This thing existed before. It's not clear what the connection is.
There's no connection.
Okay, when MacLean was inventing adjoint functors, which I happen to know because I actually was in the class when he was writing his book the first time, he did mention the analogy with this.
It's more a visual analogy than anything, I think.
But it's the exact analogy. I mean, just the guys that these two numbers are the same. In category 3, these two Hom sets are the same.
So it's that's what I mean.
It's exactly.
That's what I call visual analogy, like syntactic analogy.
Okay.
You know, actually, one ends up being an example of the other. It's not.
Galois joints are the example, but these things need a little bit more than Galois joints. This you need to. You can figure out some. There's probably some ways.
Replace numbers by sets, and then replace the product by the whole set. Still kind of there, I think.
Yeah.
I seem to remember John Bias was.
I'm sure there are many different ways.
He definitely had something to say about this. And he claimed something, in fact, quite strong, but I don't remember. It's been too long. I'm trying to remember something I read 10 years ago.
So it's contra. Yeah. So it's essentially a contravariant thing which flips the order of the composition. You can immediately see that these adjoints. So if you would take the category of Hilbert space and linear map, it's like an identity and object involution. It just flips the arrows and brings you to the off category. So It's a basic structure. It's a basic structure you got on Hilbert spaces, which you get from the inner product. So we've been calling these things dagger categories. It's just a category with an evolution, an identity, and object with evolution. And now, once you've got this notion of adjoint, then a map is what you call a unitary map is something which has an inverse and of which the inverse is equal to the adjoint. And then you can show that this is the same thing as preserving the inner product. So and then again, Wigner's theorem tells it's enough to preserve orthogonals to know that your map is actually it's a little bit subtle there. It's either unitary or anti-unitary. And then for some reason people just ignore the unitary ones. And what you refer to array.
It seems to me a multiple of the identity would preserve orthogonality.
Yeah.
But it's not unitary.
It's not unitary.
No,
Wait.
It's slightly misstated.
I must have misstated something. Right.
It's not to project.
Yeah.
Projected.
No, it's
To say that
wait, how is
to
it
say that
again?
F preserves the inner product is equivalent to saying that F dagger F is the identity. So,
right, you're right.
but then that doesn't imply F times F dagger is the identity. That's the point. So you need to assume that it's
Yeah, it's norms. You need to preserve norms.
Yeah.
Norms. You need to preserve norms. So usually, the thing is you need to preserve inner product of what is called compatible element. And compatible element means either orthogonal or the element with itself. And this then imposes the norm preservation. Yeah, am I right, Keith? You probably know Wigner's theorem, right?
Yeah.
Yeah. So, just with these concepts at the hand, like basically the state of a quantum system is described by a ray in a Hilbert space, and deterministic transformations are described by unitary operators. But that's the first postulate of quantum mechanics.
The definition of ray, you assume size non-zero, do you?
What? Yeah, sure. Yes. Well, it's
Zero isn't a state.
typically zero, you don't treat it as a state. Now,
I think I understand why you say deterministic transformations, but it deserves a little explanation. This is how the state of a quantum system can change when no measurement is made.
yeah, so typically you've got your system, and you just make sure that it's actually an active thing. You have to make sure that nobody is looking at it. The moment somebody looks, it collapses. So in the lab it's sometimes harder to get this sort of unaltered evolution done than actually the actual measurement. Because the measurement sort of destroys the system and you want to actually maintain it, and so it's not, you have to put it in a very big box just to avoid, otherwise you get all these decoherence and it just like you lose the system.
You said you won't talk about Schrödinger equation.
I won't talk about Schrödinger.
Well, this would be the point where actually Schrödinger equation
Yes.
it becomes important, because this tells you how the quantum state will change in time. And this is, you can write down a form where basically you have a unitary transformation acting on this state. This is basically if you integrate the Schrödinger equation, it's a differential equation.
Right.
I'll have it in one talk.
Yes. So Selfadjoint operators. Obviously, they're invariant on the adjoint, so they have to be endomaps, obviously, otherwise the type wouldn't fit. Well, quantum mechanics, the way it's usually told, it's very untyped anyway, so it doesn't mean that. And a projector is just the usual notion of projector of algebra. It's like self-adjoint idempotent. And then, like the key theorem you're then going to rely on is what's called the spectral theorem which is fairly trivial in the finite dimensional case, which becomes a hell of a job in the infinite dimensional case. And it says that whenever you've got a self-adjoint operator, you can always write it as a sum of projectors, as a spectral sum of projectors. So if I give you a self-adjoint operator, then I can characterize it by a list of numbers, positive real numbers, and a corresponding list of projectors. And that's the spectral decomposition. And all these projectors are mutually orthogonal. So basically, saying self-adjoint operator is the same thing as giving me a family of projectors which are all mutually orthogonal and a corresponding list of numbers, such that if you make this sum, you find self-adjoint operator there. Basically, this is just you take the self-adjoint operator, you diagonalize it. That's what you do, you diagonalize it. Then this would be the eigenvalues. And these projectors would project on the eigenvectors. And if you happen to have a degeneracy, like a two-dimensional space of eigenvectors, then this will be a projector on a two-dimensional space, on the two-dimensional space of. So this is basically the same thing as like diagonalization of matrices. It's the same thing basically. With the difference that you now write this in this form. Now why is this key? Why is this key to what we are doing? Everybody's happy with this? Yeah? Yeah?
Maybe it's a good idea to say how, for example, such a spin also, as you had earlier on, how this would look like.
Right, I had this example before. Suppose that you've got a self-adjoint operator which looks like this. Is a self-adjoint operator, obviously. Then I can write this as 1 with coefficient 1, 0, plus 2 times 0, 1. So remember my example, like these two examples of projectors. And so here there's just these coefficients which are the eigenvalues. So this is the spectral decomposition of a very simple self-adjoint operator. And you see these two things are orthogonal, because if I multiply them I get 0. And if I add them, if I add this sum together, I get this 1. So now, here is the reason I've been introducing these things. Postulate 2 of quantum mechanics. A measurement on a quantum system is described by a self-adjoint operator. We call these values 1 and 2, we call these values the measurement outcomes. And these projectors are the ones which actually describe how the state changes. I had this two-dimensional example before from the sphere. You remember I said that it either projects up or it projects down. It projects on this value or it projects on this value. That's the way it works. So okay, let's be more concrete about it. So you've got a system in an initial state, and then the measurement takes place. So what happens? The initial state changes to the projected version. Suppose if the initial state would be Z1, Z2, this projector happens, then this will change to, well, if you project, then you get Z1, 0, but since quantum systems are only defined up to a global complex number, I can change this to 1. That's what happens. The probability that this happens is given by this inner product. So that's the probability which it happens, where you take your states to be normalized. And then there is this funny thing, and this is like the observer which performs the measurement receives the value AI as a token witness of that fact. So this thing happens, and then you're doing your experiment and you're looking at your meter and you get this value, click it. And then you know which measurement which of the projectors has happened. It's a very weird thing. So you push a button, you say start measurement starts, and then you get this meter reading and it says, oh, this projector happened. That's basically what it is.
Just to mention, because I'm needed later on, the fact that the probability of this outcome is calculated that way, and that we obtain one of the eigenvalues as the measurement outcome, this is called the Born rule, with respect to Max Born. And the fact that the state changes according to psi goes to pi psi, and actually it must be normalized. Again, this is so-called projection postulate of phenomena. Right. And about both things you can find in our library, I guess.
Yes. So this weird thing is the source of all the problems which are referred to as measurement problems. Why does this happen? What causes the non-determinism? So what is this role of this observer there? Who is an observer? Is an insect an observer? are only humans, observers,
Or PhD students.
or maybe not PhD students. It's like this is like an unfinished business. It's completely unfinished business, and nobody. So there is no consensus about what is an observer, like what causes the collapse. Well, people do this in the lab, and then they have a big machine and they push the button, and clearly they were an observer because the thing happens. This is what happens. This is what they observe, not what they observe. This is the phenomenon which happens. So this is the whole cause of all the fuss, because it's weird, but it works. It works. It's like this is the most successful scientific theory in terms of experimental predictions ever. You find, I don't know what the list now is of the sort of digits they can do in quantum electrodynamics, but it's about 11 digits, I think. These are experimental predictions up to 11 digits. This is just amazing. And this is from this sort of rules. So
Actually, it's also useful to list all the things that you couldn't understand without quantum mechanics.
yeah.
Like why the atom is stable,
Yes.
why matter has color.
Yes.
I mean, when you get down to it, you can hardly understand the damn thing without it.
Yeah. So this rule is very important. And people don't like it. People just don't like it.
And one more thing, it's also a very good instance to see what you said very early on. If you measure and have these two possible outcomes, if the state is very close to the one direction, and with high probability this will happen.
Yes.
You can see it here.
Yeah, right.
Psi can be written as a linear combination of eigenstates of the
Right.
observer.
This would be if this would be very close, meaning that this vector would be an eigen state of eigenvalue 1 of this projector. That means very close. And then this inner product will be very close to 1, because this will just project on itself and you just get a norm which is 1. On the other hand, if this guy is like orthogonal to the vector this projector project on, then this thing becomes 0, the 0 vector, and the inner product becomes 0. So that's how it goes. So here is a remark, like what are these values AI which the observer gets? Well, for the story I'm telling you here, they actually don't mean a lot. They are just token witnesses of which of these projectors happens, basically. They just tell you. Now, if I take this Selfadjoint operator or this Selfadjoint operator, you substitute just the value AI by I. It's kind of the same measurement. There's no difference there. It's just that the values you get are basically regauged. They're different. But you know which value. Here you know that I corresponds to Pi, there you know that AI corresponds to Pi. But it's not an essential difference for what happens to the system. So in a way, the essential thing are these projectors, this list of projectors, or actually it's a set of projectors. The order doesn't really matter if you sort of tag them individually. So that's the essential thing of the measurement, not the Selfadjoint operator. For one, if you take this, if this is an operator, and a Selfadjoint map, and I compose this with another Selfadjoint map, then of course, compositional intuition would make you think this is like first doing this measurement and then doing this measurement. No, this is not a measurement. Formally, this is not a Selfadjoint operator in general. It's nothing. So composing these Selfadjoint operators basically means nothing. So the real things which you compose are these projectors. This is really doing one measurement after the other.
Well, they do have the Jacobi product.
Right. Right, yes, okay. Yeah.
And they form a Jordan algebra.
Yeah, okay. So, well, if you see star algebras, of course, they use this composition. It's the composition which lives in the star algebra of observables, but it makes you think about, is this the appropriate formulation?
To give a picture, quite an operational picture, changing the AI, it's like rescaling, like changing the scale and measuring it.
Yeah, just putting different numbers on your meter reader. Or just changing from centimeters to yards or something. These things I still don't know.
What about if you change it so two has become equal?
What?
What about if you change it so two unequal ones become equal?
But then you've got a different beast, of course. That would be a completely different measurement. You need to distinguish those which were distinguishable. So a trivial measurement would be the identity. It's doing nothing.
Oh no, but in general, most measurements in more complicated systems have what's called degeneracy.
Yes.
So,
So this-
the eigenspace is usually, I mean,
Some of them would, so these projectors are typically not one-dimensional. They have like higher dimensional space of eigenvectors.
so people talk about complete sets of commuting operators. That's just a physics for basis.
And later on talk about the common checker theorem, exactly such questions play a role, so maybe we can come back to the question then.
Right. So I need to rush a little bit because I want to give at least proof of teleportation and some of these things. So who doesn't know the tensor product of Hilbert spaces here? It's one of these delicate things. Do they teach it already in maths now?
I learned it quite late actually.
What?
I learned it quite late. So.
I know, I remember when I teach this course, there's a lot of mathematicians in my class who don't know it.
Depends which courses you
It depends which courses they take, I guess.
So is there any difference from the tensor products of ordinary vector spaces?
Right, yeah.
In the finite dimensional case, it's not very different.
Yeah. So I think the essential thing to pick from this is, if you take the direct, so there's two canonical monoidal structures on the category of Hilbert space. One is of course a direct sum. And this comes with these canonical injection maps. You know, direct sums are just pairs of states. And then you've got a canonical injection map of state of one system in the direct sum of two systems. The thing with a tensor product, which I write down here, don't try to raise, because it's basically what you take is you take all formal linear combinations of pairs and then you make them subject to some congruence relation which imposes it to be bilinear. Or it has some universal property which defines it too, which you find in any standard algebra book basically for finite dimensional case, which is very close. But it doesn't have this sort of maps which inject the original state in the tensor product. And this basically has to do with the fact that a tensor product, the states you shouldn't be thinking about of pairs of systems. That you should, and I'm just gonna throw one of the, I think the easiest intuitions to see that is that the basis of the direct sum is basically the disjoint union of basis vectors of the underlying spaces, while here you make the Cartesian product of basis vectors. So you got the following fancy rule for the dimension. Instead of the dimensions adding up, dimensions multiply. And this is like this gigantic blow up of the size of the state space, which you get for a tensor product, which you don't have for the direct sum. But there is some, so you got the inner product rules. So for the direct sum, you would just add up the inner products. For a tensor product, you multiply them. Now, if you think physically, I've got two systems, and I know my inner product gives my probability of this one and my probability of this one to be realized. It's sort of normal that they should multiply, because the probability of something happening here and something happening here is their product. So there's something normal about why you would use a tensor product to describe this, because this would physically make no sense whatsoever. This sort of rule to calculate the probability. But I think I wouldn't care too much about a tensor product in the way it's usually defined. I think this is the essential definition of a tensor product. Basically what I write down there is that, and this is actually also I teach it you. The tensor product of two Hilbert space is just a space of linear maps from one to the other. That's it.
Which linear maps?
All linear maps.
So it's working in finite dimensions.
You have to add to the conjugate.
You're right.
Yes, yeah. I'm keeping it all Hilbert-Schmidt otherwise. Infinite dimensional, you need to restrict to Hilbert-Schmidt maps.
Right.
Whatever.
Sorry, yeah, you're right.
Yeah. Finite dimensional, it's easy. So basically, instead of thinking of trying to combine states with one of the other via some free construction, just think of the linear maps from one to the other. And these things, you remember these pictures that I had? Don't think about this as one system and another system, but just think of it as a linear function from one system to another. And in all the applications you're going to talk about, this is a much simpler view of tensor products. So just from the start, think of it as a channel which connects one system to the other. It's a very easy sort of intuition. And this is perfectly, why is this true? Well, for those who know tensor products, you just write down, if I've got two bases, say basis y and basis j, then tensor product just means putting a bunch of coefficients there. But these coefficients, if you put them in a matrix, you get a linear map. That's it. That's it. So that's a correspondence between linear maps and the tensor product. And that's all you need. Now, there is an issue here of putting here the conjugate.
Actually, if you're going to ask mathematicians if they know this, you should ask them if they know about the tensor inner product spaces, because that's what you're really doing here. Because the tensor product of Hilbert spaces is a very tricky thing in the infinite dimensional case, because you have to pick a topology, and there's no one right. I mean, it's a whole, so if they say no, that might be what they mean.
I'm sticking to finite dimension because usually when you get into a mathematical physics course and you need to deal with infinite dimensions, you spend 90% of your time on these sort of subtle issues. So I'll just try to...
So how do you pronounce that symbol, the lollipop symbol?
Lollipop.
Lollipop.
Okay.
So this notation comes from linear logic. It's, you could put also an arrow, but just to emphasize.
So for qubit you would need just 2 dimensions.
What?
For qubit you would mean just
For
2
qubit,
dimensions.
this would just be the linear maps from 2-dimensional to 2-dimensional. That's like qubits are a little bit a bad case because the direct sum has the same dimension as the tensor product.
But for
2 times 2 equals 2 plus 2.
But what is like physically means that you cut off number of dimensions? Like with normal bit is clear, like signal, no signal, and for qubit is something similar. How you make right two? If you just take a spectrum decomposition, you have a lot of things, right? And so should be a way just cut it to 2.
Spins just automatically come in
Yes.
places. The total spin of the particle is some finite number. And then when you measure it in some direction, it can be anything from plus that to minus that, but that's all. So it just automatically comes in finite dimensional Hilbert spaces. If you try to apply this now to the rest of quantum mechanics, when you're looking about the orbital of the atom, then you're putting in some sort of energy cutoff, which could arise in various ways. But this kind of mathematics is usually not applied to that kind of problem. It's in spin geometry is where it comes in.
Yeah, but one of the best experimentally usable examples is like photons, which have 3 levels. They have 3 levels, x, y. So you got 2 polarizations like that, and then only.
No, photons are transverse.
What?
They only have 2. They're transverse.
Yeah, it's transverse. Yeah, sure. So anyway, the joint state of a compound quantum system consisting of 2 substances is described by the tensor product of Hilbert space, which describes 2 substances. That's what I've been working towards. Right. Okay. Now I want to give. Yes. So right. I'm gonna skip this.
Sorry, can you put this on for a second?
Which one? Previous one.
The tensor product is assumed to be commutative.
Symmetric. Yeah.
And then, but if it's not, then the logical linear implication is again you have 2.
Then you have 2. Then you would have 2.
It's possibly a little confusing because the joint state is of course one vector in the tensor product. The state space is the tensor product of the spaces.
The joint state of
And
is described by meaning it gives the space.
Okay.
It's described by it should say instead of by within. Probably. Probably I said by because otherwise it just didn't fit on the line.
The way you want to go is really you want to show some states which are not product states.
Right.
So
I'm gonna get. Yes, of course I'm gonna get to those. So here are some examples. Which have famous names. So the first one is what's called the belt state. You've got 2 elements in your pair. This is like I used another notation here. So basically this corresponds to this linear map. I said there is a correspondence between the tensor product states and linear maps. So the Bell state is the one which corresponds to the identity, where you think of this channel as the identity. The EPR state would, for example, correspond to this channel.
I would call the EPR state the Bell state.
I know that people mix up these names. So EPR is Einstein, Podolsky, Rosen. So people, yeah, I think historically it was this one because this is the only state, because this is an anti-symmetric one. So this is the one which obeys a fermion. But this one is of course more natural just because it's the identity. It makes it easier to compute it. Now what you can do, so then it's mathematically simple to see that you've got certain types of correlations. So if you pick these two states, like firstly I'm not going to go into it, but it's very easy to see there is no way you can write this state in the form psi. It's a very easy computation. To show this thing you can never write like this for any choice of vectors, never. So it will always involve a sum of two components. Because if a state would be writable like that, it's actually a sort of trivial channel which doesn't really communicate anything. So this state always will have, what people say is the moment you've got a sum there which is irreducible, then you call it an entangled state. That's the definition of an entangled state. It's a state where there is a sum which you can't avoid. So you can never write it in this form ever. Because this would be the sort of things you describe in the direct sum. It's a Cartesian product of two things, just one state and another state. The sum is actually which makes the difference. And now we can see this. So suppose we've got a system in this state, yeah, and we measure the left system. So we've got, so here is my thing.
So these are the ones to blame that we cannot, that the tensor product is not the Cartesian product.
Yes, these are ones which you can't fit in a direct sum representation or anything like that. These are the ones which you can't describe as a state of this system and a state of that. The moment you've got this sum here, I can't say like which state the first system is in. It's not this one, it's not this one. It's a weird combination. So you get. So if you don't want to think in terms of like complex coefficient, you can think of this as a set of two. So you can think in relational terms. In relational terms, it would mean this basis vector is related to this basis vector, and this basis vector is related to this basis vector. It's not the case that you just got two ones. You got a relation between basis vectors. And here we see what happens then. Suppose we've got a system in this state. Suppose we've got a system in this state, and we decide to perform this measurement. This is like a measurement on the first system. So I measure this system, and there's two possible outcomes. Yeah? And these are the projectors I'm using. These two. Suppose I get the first outcome, right? Then one of these two sum terms will vanish. Suppose if I project on the vector E1 in the first system, then this term will vanish because it's orthogonal to E1, this first component. So the only thing which remains is this one. If I observe this guy, then the only thing which remains is this one. Yeah? Now, but you see, once I've done this measurement on the left one, and I've got this state, when I measure the second system, I will for sure find E1 on the second system. If I find this one and I measure the second system, I will for sure find E2. So these two systems are correlated. Whatever outcome I will find on the left, I'll find on the right. Yes? Which clearly says that neither of these two substance systems are a definite state. Because if at one side I find one outcome, I find the same outcome at the other side. So they are perfectly correlated, but they have no identity besides that before you actually do any of these measurements. So it's really, it's a channel. It's really a channel. It's a perfect correlation between two systems. If I find one at one side, then I find the same one at the other side. And if you would do that, like for this state, you would find some sort of anti-correlation. And if you find up at one side, you find down at the other side.
There's only two?
No, there's two. You can put in any number of complex coefficients here. Yeah?
Okay, it's slightly confusing to say it's the because there's a plus. Because if I change basis...
Sure.
So what's invariant here is the determinant of the matrix. And in fact, it's rank. So one state is rank 1 and the other state is rank 2. That's what's really invariant.
So the essential thing is that there is no way of that you can write in this guy, like what I said before. That's the essential point. Louis is pointing at it. Many of these guys you can't write like this. That's the essential part. Because of course there are cases where you would find, if I change the basis of this thing, it would look like sum suddenly. It means the point is that the sum you can't get rid of it by changing the base. That's the essential thing. And in linear algebra terms, it means the linear function here should be non-degenerate. It should have zero-dimensional kernel. If there is a zero-dimensional kernel, then it's a genuine channel, and then it's an entangled state. No, what was I wanted to say something. Right, the question was how many entangled states you've got. Well, you have got a matrix A, B, C, D. Then this basically corresponds to A, 0, 0, plus B, 0, 1, plus C, 1, 0, plus D, 1, 1. So for each matrix I've got one of these states. Some of them won't be entangled states. Most of them will.
The condition is that the determinant.
Yes.
Vanish.
Yeah.
And then you have to...
It should be rank 2. If it's a rank 2 linear map which you got here, then this is genuinely entangled state. If it's a singular linear map, then this is a disentangled state. Or they say disentangled. So, but all the ones which you can't get rid of the pluses are the new stuff which you don't, which is really the new stuff which enables you to do all these protocols.
But someone said there is only 2 up to...
Oh, no, well, I know there is actually a continuous family of qualitatively different ones. And the qualitatively different ones mean that there is something which people call maximal entanglement. It basically means that, like this is a maximally entangled state. It's sort of a maximally optimal channel. So you could imagine that, for example, so let's write this down. Right. So if alpha and beta are equal here, then you find this Bell state, yeah? If alpha and beta are equal, then this one, yeah? Now suppose if alpha is really small and beta is very big, then this becomes very close to this one. And then it's like a very poorly entangled state. Ultimately, when this term vanishes, it's a disentangled state. Because then it's just a pair of 2 base vectors. And you don't just think of this as one, and so on. So there's a continuous family between maximally entangled. And by the way, as a comment, understanding the structure of entanglement for higher than 2 dimensions is an open problem. Like fundamentally understanding which qualitatively different entangled states there are in higher dimensions is a completely unsolved problem. People don't have any good ways to classify them. Dimension 3 is sort of understood, but there's probably more things to be said about that.
There's also a number of suggestions how to measure.
Yeah, but the reason that there is many suggestions is just a witness of the fact that it's completely not understood what the structure is.
And in the protocols, when they say entangled, then you maximize.
Depends. Typically, you can depends. Like in teleportation, you assume maximally entangled. But if it's not maximally entangled, you can usually find ways to tweak it. Like there's tons of paper written because in practice you would assume that you never have maximally entangled. In an engineering situation, you will always have lost some bit of entanglement. So you have to deal. So loads of papers are written about the non-maximal entangled situation, how to deal with it, how to correct it, things like that. Ideally, you want to talk about maximal entanglement because it's the identity. It's so simple to compute with. Right, I still want to get to teleportation. I can't think. Yeah, I should get there. So just mention. I think this is important. let you know about this thing called Dirac notation. So for a long time, Dirac notation was conceived as merely a convenient notation, and sort of even mathematically unsound. I'm not going to discuss it, but there are some problems with Dirac notation in a lot of textbooks. Now, actually, if you like category theory, it's a nice thing because it brings you closer to category theory than the usual mathematical formalism does. So just think of a state of a Hilbert space, like a vector in a Hilbert space, as a linear map from the complex numbers into that Hilbert space, which sends the number 1 onto that vector. Yeah, yeah. There's clearly a bijective correspondence between states and vectors in a Hilbert space and linear maps, which are defined like that, because the image of the number 1 determines the linear map by linearity. Yeah, it's clear? Yeah. And now there is this thing called Dirac notation, and this is what physicists would call a ket vector. And that's what I want to interpret as this linear map. And what I call a bra vector, you want to interpret as its adjoint. And then they have this thing called the bracket, and that's the composite of this thing, and you see it's the inner product, a bra and a ket. So basically the whole idea is to chop off the inner product in two sides, this side, and give them some individual way of existing. It sounds a bit weird to chop up the inner product in two ways, but if you interpret your vectors like this, there is no problem with it. It's a composite of linear functions here. Huh? So it goes from the complex numbers into H, and then back into the complex numbers. So it gives you a linear map from the complex numbers to the complex numbers. What is a linear map from the complex numbers to the complex numbers? It's a complex number. Because if you know the image of 1, you get a single complex number. So when you feel it's becoming more categorical here, you're reasoning about functions and morphisms. And that's like the natural way to interpret Dirac notation, I would say. And right, so then a projector, for example, would be a ket bra. So a projector you want to think of it this, so it goes from the Hilbert space into the complex numbers into the Hilbert space. And this is how you can write down a projector in this sort of Dirac notation, and then you can apply linear maps to it. Okay, just get on. I'm not going to rely too much on this. But why physicists like this notation is because it's sort of convenient to treat really these kets and these bra vectors as individual entities. For example, since like this would be my projector on the state phi, and I write it like that. So I want to compute in the product value here of this thing. I want to compute. You remember this is the value of the probability for a measurement to take place. So I now plug in this thing here, and you see these two inner product terms appearing, one conjugate from the other. So this is the inner product term. If I want to see whether two projectors are orthogonal, so here is one projector, there is the other projector, just whenever this number is 0, which appears in the middle, and which is an inner product. So there is this swapping between what is a projector and what is an inner product by chopping up both the projector and the inner product in this ket part and this bra part. So if you read a paper by physicists, this is how they calculate. So they are not realizing this, but it's much more compositional than you would actually do in standard linear algebra in a way. So this is just to mention that. Okay, so now I'm going to prove quantum teleportation to end with. This iron pieces of paper. Right. So this This is, for example, the standard basis of the tensor product space, of course, because I got a space. So you want to read this as just the tensor of base vectors of the two underlying space. So this is how you would build up a standard base in a tensor product space. You take the base of one of your subspace, you take the base of your other subspace, and just multiply the base vectors and get these four. Now, a more interesting one is this guy. You see, these are all entangled states. And if you check, you can see that they actually effectively are all mutually orthogonal. So if you take the inner product between all these things, you will get 0 all the time. So this is a different base, and they refer to this as the Bell base usually. In the correspondence with linear maps, they correspond to this matrix. We saw already that this one corresponds to the identity. Yeah? So 0, 0 is 1, and 1, 1 is 1. If 0, 0 is 1 coefficient, 1, 1 has minus 1 coefficient. 0, 1 is now a 1 coefficient, and 1, 0 has a 1 coefficient, and here the minus 1 coefficient is from the 1, 0. Yeah? So you see that this is the tensor product states, these are the corresponding linear maps. And the teleportation problem, this is clear what these things are. This is just a base of the tensor product and corresponding linear maps. Then this is what how the teleportation protocol effectively is prescribed. So you got your first qubit, which is in a certain state, and the second one and the third one are in the Bell state. I probably should pick up the picture again, which I started with. Right, here it is. It works? Oh, it sort of works. Hi.
This is an example of the superposition.
Very much so. So okay, I'm just going to swap them. So you see, the first is in some state, which is denoted by psi. The second one, this thing is the Bell state now. Bell state being this entangled state. Yeah. Then we perform a Bell-based measurement of the first and the second qubit, which is a measurement against this base. Yeah? So these are projectors. The projectors which will change the state are projectors on these vectors. And then, when we obtain the outcome, then we perform the transpose of the corresponding measurement on the third system. And the claim is that if you do all that, whatever state will be here will end up there. So this is the protocol. I could come. Right. Let me prove now the board. Usually when you see this in the textbook, then they just start to multiply all the matrices corresponding to these things. A slightly more elegant way of doing that. The first way to do is by proving the following lemma. That if you take the Bell state, like that, then this thing as a whole is the identity. That's my claim. How do you see that? So I'm going to introduce a little bit to really understand these things. The only way to understand and see these equations is to sort of introduce some picture notation. The picture notation I will use is, I will represent such a Bell state by a cup, and I will represent the edge joint by the thing upside down. And then this equation, basically, in some sort of graphical representation like that, can actually be represented as follows. You see, I've got a Bell state here. I've got an identity there, which I represent by a line. Yeah? So this thing is this Bell state. This thing is just the identity. Now, I take the corresponding bra and I represent this by this. and I plug in the identity there, which is this. And the claim is that this thing as a whole is equal to the identity. How do I prove this? Well, let's fill in this. So we got 0, 0 plus 1, 1. Tensor identity composed with 1. This is actually the whole core of the whole thing. This lemma, everything is in here. Right. But so how do you compute such a thing? It's a bit of mess. The whole point is you try to write something on a line which actually more naturally fits in the plane. Because you've got this tensor which is things beside each other and this composition which is things after each other. So this is actually how you don't want to read it. But formally this is. Now let's compute it. So we've got, this is actually a tensor product of 3 systems we're talking about here. You've got here 2 systems and then a third system, yeah? So we're talking about 3 spaces. And now we have to compute this thing. Now there are some inner products going on here. So this is system 1, this is system 2, this is system 3. So this is system 2. This is system 2, this is system 2, this is system 2. Yeah? And we got 2 sums, so we got 4 terms. So if I take in a product of 0 with 0, that's 1, that's the number 1, that's okay. If I take in a product of 0 with 1, I get 0. So the only terms which are going to survive are this one together with this one, and this one together with this one. This one multiplied with this one, then what remains is this thing together with this thing. Wait. This one together with this one. Now this is on the third system and this is on the first system. So they don't cancel out each other. Basically what I get is this. Similarly from this term we get this. And this is basically the identity. This is the projector on 0, this is the projector on 1. So this is what you write. 0, 0. This is what you write. 1. And so this is the identity indeed. So we have established, so graphically we have established that this picture is equal to this picture. Yeah. It's clear? Yeah? I know this is horrible notation, this is just not the right way to compute with these things. This is the way it's done. I know, it becomes complete. The moment you start mixing up tensor and composition, you get a complete mess. It just messes up. And I'm not doing teleportation. If you do entanglement swapping, it becomes completely impossible because you're sticking in things in the middle of other things. So, but this is what you find in textbooks, and it's horrible. So this is obviously how you're going to read this equation. So this is the key equation here. And we get that. Now there's a second thing we can prove. So there's a second lemma. So this was lemma 1. Now we prove lemma 2. And formally lemma 2 says that you have got a linear map and I cancel it with the identity and I apply it to the Bell state. Then this is equal to applying to the other system the transpose of this linear map. Let's write this down again in this sort of form. So at both sides we got a Bell state. These are the substances. That in one case you apply a linear map F here, in the other case you apply the transpose to here.
So it's not the actual.
It's transposed. It's transposed. It's transposed. Yeah. Now that's an assumption. That's why you've got both. You need both to describe complex Hilbert spaces. Yeah. So this is what we're trying to prove again in the same vein as we had this one. How do you show this? And you see You see this immediately why it's transpose then of the edge joint. So let's write this out in matrix notation. And so the belt state, I'm just going to write it now with an indexation. Is this thing? That's the belt state, yeah? Just an indexation of 0, 0 and 1, 1. Okay, I'm going to apply this guy now, which means we've got a linear map F applied to the first component. Yeah? I can write down the matrix of this thing. Right? Just writing down the matrix of this linear map applied by and now we're going to play the transpose. What is the transpose of this thing? Well, the transpose of this thing is just exchange the indices. I put a T there. Just swap the indices. And then you see by symmetry, this matrix can be now swallowed in this guy. So I get sum over J, F, J. So you just use the symmetry here, the transpose to swap this factor to the other side. This results in this. So we now established indeed this picture. Right. Okay, back to teleportation. These guys are let's throw away this one. Okay, what is teleportation? Teleportation is we got a belt state. So we got some input state, the green thing there. I'll just try. So this is some psi state. I've got the cut which I decided on to denote like this. Yeah? Then I apply this thing, and now I have to go back to this slide. So we're applying measurements. We're going to apply these things now as brass. So one of these projectors on this state is going to happen. Now, what is this state? This state you can easily see is that each of them is actually equal to this linear map having been applied to the second component. If I take this state in the belt state and I apply this linear map to the second component, then this one is going to become -1. If I apply this one to the second component, then the 1 is going to become 0 and the 0 is going to become a 1 and I obtain this one. If I apply this one to the second component here, then this 0 is going to become a 1 and this 1 is going to become a -0. Now, the game I'm playing here is just if you've got a linear map F, then if I write down this, then I get a corresponding entangled state. You see, this is a linear map. This would be, say, a linear map from A to B. And here I've got an entangled state from A to B just by plugging in this belt state here. So what I'm playing there is this correspondence between linear maps and entangled state. This is literally what we write down, as A, lollipop B, is isomorphic to, well, I'm not going to, let me just forget about the star for a second, it's important. Basically, this correspondence is just this correspondence. Yeah? And you see that, why? So it's clear that you can go from here to there. Why can you come back from there to here? Because of this guy. He allows, this thing that becomes the identity allows me to put it there and then replace it by the identity. And I find this guy there. So just this little law which I proved here, establishes really that we can identify linear maps with entangled state just by putting this little belt state underneath. So this is the trick we are now going to use to encode this thing in our picture. So right, so the belt state applied, let's call these correction maps, these 4 correction maps UI. So this would be one of those 4 vectors, where what I call UI would be respectively these maps. And I'm going to denote the adjoint just by putting this thing upside down. The adjoint would then be that this guy becomes the adjoint. So this is now this PI from our pictures. And then the last bit we have to plug in is this one. And in my protocol I described that I wanted to take the transpose here. So this is the description of teleportation. This is the same thing as what is in the picture there. Now, applying our lemmas, we know we can take this guy and plug it here. We use this, right? So we can erase this one and put it at the other side, provided we transpose it. So it was the adjoint, and the transpose of the adjoint is the conjugate, component-wise conjugate. And now the component-wise conjugate and the transpose, they are each other's inverses. So one is the adjoint of the other, and if they're both unitary, they cancel out. So we cancel these things out. And then by that one, this thing is just the identity. Yeah?
And what corresponds to phone call, the classical?
What corresponded to the phone call was the fact that, I'll go back to my initial thing. So here I got new adjoint. Yeah, it's almost like cheating. The fact. So here we have the fact that these indices are the same. This index is the same as this one. So otherwise they would never cancel out. That's the phone call.
I'm also confused with a related question is what happens in this photo? Yeah, you got those 2 little grey lines which say that R2 that made the measurement.
So that's actually where the Dirac notation comes in. A projector is this thing. A projector is this thing, typically, in this Dirac notation. But for this protocol, you actually use only this part. You don't care about this part. I could actually, the other side would be if I just put here UI adjoint, then this as a whole would be a projector. Now I only take sort of, it's a very weird way, but I only take half of the projector. You see what I mean? A projector, the projectors PI decomposed, they're equal to these 2 bits. And you actually only use half of it. It's the effect, it's the collapse, it's really the collapse effect, which you could say it's almost a backward effect of a projector which causes this thing to flow back. You see? So I like to denote projectors like this, like graphically. So if this is a little trick, but no. So if you take the Dirac notation like this, yeah, then you can sort of close these triangles. And if you then rotate it like 90 degrees, you get a picture like this. And we think of this as the state, which I've been using here. And this is actually the only. And as a whole, this thing is a projector. Because if I compose this with itself, it doesn't need a lot of space. This is basically the same thing as Dirac notation. If I compose such a thing with itself, and this thing is normalized, then this is 1, because it's just the inner product. So it's a projector. It's an idempotent.
It's just that in the interpretation of quantum mechanics, like these are non-determinist processes. So what you've really got is you've got 4 diagrams. Say, in the event that happened, then this diagram.
Right. You got 4 in the event there is a condition, there's quantization, quantification here. Yeah. You've got 4 diagrams. One of 4 scenarios happens, and the correspondence lies in these indices here. That's why we use Frobenius structures for dealing with these possibilities without having to write I. That's where the Frobenius structures come in. Yeah, I think that's it.
Yeah. If only I would like to add a comment from a physical perspective. I mean, usually entanglement seems very strange because it has these non-local effects. And I think this is a very neat way to reformulate this and understand this categorically. But it seems to add actually a non-locality or in time additionally to this.
Yes.
Which, for me as a physicist, is an additional problem to a certain degree. I see it's very neat mathematically.
It's not a choice. It's what this is just.
I know. I understand this perfectly. I just want to say that there are different ways of looking. The mathematics is very neat, and if you still don't see what's going on physically, I'm with you on that.
But what do you mean non-locality?
Sorry?
What you meant by time non-locality?
Well, it's the idea. Like if you follow this line, it's as if you tend to treat as if the information flows backwards in time.
Yes.
So it's acausal. Like you can see the line sitting in here, and this goes back. That's how the information flows. That's what this thing tells you. But that's what Hilbert space tells you. This is just Hilbert space. There's nothing.
Contradiction.
This is just plain formal quantum
Well,
mechanics.
you just as well say that there's information in the combined state that you made there.
Right.
I mean, and of course, if you didn't make a combined state and sent one half of them one place and one half the other place, you can't do any of this.
Yes.
So, you could have sent information to UI just as well instead of making a combined state by just sending a bit, and it would have spent the same amount of time and you've gotten the same information there. So it's not, there's nothing mystical about the way information flows here.
So the thing you want is, if you want this picture to make complete, you have to put a line here, which is the flow of this data to this data. This sort of restricts the causality of the thing very much. And what you structurally want to understand is this is the subtle thing I mentioned before, that you just can't send information back in time and these things. It's just that you can't do these things, and you can't send information faster than that. And the whole restriction lies in this bit of structure. So understanding how this is about classical quantum interaction, how the classical structure and the quantum structure interact. And that's what you really want to understand about this protocol. Why? It's so seductive to think, oh, now I can do all kinds of crazy things, but you can't do a lot of crazy things. It's like very, very sort of well balanced between not being able to. The moment you don't send this, you can prove that the moment you don't do this correction, then you've got zero information on this side, zero. It's completely uncertain, maximal uncertainty. So it's all about this correlation. So yeah, just for people, so basically for people who know category theory, you see, this is just compact closed categories. So structure is what you use here is compact closed structure of Hilbert spaces. And then there is this subtle thing that you do essentially have to also bring in these extra structures to account for the adjoint, which is not a transpose. Because compact closure gives you the transpose. Yeah?
There was no entanglement.
What?
There was no entanglement.
You don't have these connections.
Then the tensor product becomes Cartesian.
Yeah.
Then there are in classical mechanical.
Yes. Well, there's not a lot of classical mechanics. What people would call classical mechanics when you take a course of classical mechanics is all about evolution and equations. So there's not a lot of this which is actually even worth mentioning then even. Because it becomes completely trivial. So basically what this story tells you, you just strip away all the dynamics and all the things you care about in classical mechanics, and you just leave over what is actually very particular to quantum. So if the moment you cut down, this is just about the tensor product and nothing else basically. This picture is tensor product, nothing else. It's like everything thrown away except for one essential component of the tensor product that you can think of it as a linear map. That's what this abstract structure does for, well, it's not abstract, it's just a way of proving teleportation, which I think is more insightful than what you find typically in textbooks. In textbooks, then we just start multiplying matrices, and then you see the end state where it was the beginning state. And that's it. Yeah?
There's an interesting physical point here, which is that there is no classical theory of spin. I mean, there's a classical theory of angular momentum, but the intrinsic spin of particles doesn't fit into it. There's no classical theory of the spin of a particle that you can quantize and get, particularly fermions, which is what you're doing here. Fermions are just very, very weird. I mean, Pauli once, when they were sitting around trying to figure out how to work out the physics of spin, after they'd tried everything they could think of that made sense, he said, as a joke, he wrote down his matrices. And so the quantum theory of spin was originally conceived as a joke, because it seems to have nothing to do with the physical thought at all. But it's right, and it gives you all the right answers. Oh, there's a discussion of this in Feynman's lecture series. If you want the chapters on the Stern-Gerlach experiment, if you want to put the physics in and very concrete like that, that's a really wonderful discussion of the same thing.
But mathematically, what I see is that the tensor product is length for quantum.
Well, blame.
Because
No, but you're perfectly right.
and if you throw away the spin,
Classical physics is the exponential of quantum physics is the exponential of classical physics. In classical physics, you add. In quantum physics, you multiply. And so the vacuum is the additive inverse, so it's zero. So classically, when you've got a vacuum, you've got nothing. Quantum mechanically, when you add the vacuum, you're multiplying by 1. So how many states are there in the vacuum? Classically, 0. Quantum mechanically, 1. It's called the vacuum state. And actually, if you try to understand quantum field theory, everything revolves around understanding the vacuum state. What you've got when you've got nothing.
It's really that from additives to multiplicatives in logic. What?
The tensor Nonstarters. You throw away the entanglement, tensor product Nonstarters product, linear logic classical.
But unfortunately, there is no classical.
It would be more, like you know.
Physical classical counterpart.
That's right.
Like from the logical side, it's a bit different because so if you go to linear logic, when you go actually to these tensor structures, then you got this collapse of your negation becomes self-dual. Like if you look at Hilbert space as a model of linear logic, you got your multiplicative structure, your tensor, but which is self-dual. So it's its own negation. And you got the additive structure, which is a sum. And actually the passage from classical to quantum is actually, like Lou said, from sum, additive to multiplicative. And so from direct sum in vector spaces to the tensor product. That's basically the passage. Now there is a subtle point here. If you look at, because a lot of the stuff I've been talking about, like this, you don't need quantum mechanics for this. If you just go to stochastic maps, classical probability theory, then you can find these correlations too. But there's other categories which are compact closed, like categories of relations. Is compact closed relative to the Cartesian product. So this is definitely not the whole story of quantum mechanics in a structural way, like category logic. It's not the whole story at all. You need to know what is, because once you got quantum, you also want to say what is classical relative to this quantum. Because physics, there are these classical things like measurement. Measurement is sort of the interface between a classical and a quantum. Whether you want to lie, that's at least structurally what it is. We don't really understand conceptually what it is, but at least structurally that's what it is. So you want to also have a handle on that. And then you go beyond linear logic almost, I think, because you need to have this, like something like complementary observable doesn't exist in linear logic. It's not a concept which is part of the structure.
So are you the people who think about this in terms of logic, are you interested in quantum logic at all?
I used to do quantum, that's my background.
That's your background,
That's my background. So I think linear logic is much more the quantum logic than quantum logic. Well, you need to, the thing is quantum logic accounts for incompatibility, while linear logic doesn't. So you need to find some nice blend of the two. The incomparability part of quantum logic and then sort of more tensor structured part of linear logic. I think you need to sort of find a blend of the two one way or another.
So there is a variant for compact closed category, so it's compact linear logic. But
compact, what do you mean?
No, the only difference is the closed logic.
So then it's bi-compact linear logic.
But the issue which I didn't emphasize here is, well, I really should make this point, because otherwise you might go away with the wrong idea. But it's really very essential for quantum mechanics, which didn't maybe come out, and which definitely is going to come out in things Andreas will be talking about, like in Bell experiment, is that you got this base, 0, 1, but you also got this base, plus minus. And when you measure in this base, after measuring in this base, then you got maximum certainty on the outcome there. So these things, when I've got all the information about whether I'm in plus and minus, I've got no information whether I'm in 0 or 1. And this is the start of quantum mechanics, position and momentum. This would be position, this would be momentum. You can't know both at the same time. If I know whether I'm here or there, I know nothing about being here or there. And that is I think that's one of the things which structurally quantum logic tried to capture and didn't do it very successfully. They said, well, if you got this sort of thing, then your lattice becomes non-distributive. That's the Birkhoff von Neumann. But I think very little success has been obtained in what are the capabilities of this complementarity. What can you do with it once you got it available? They basically told you what you can't do anymore. Which things break down. Your logic just suddenly you lose something like deduction theorem. What does it tell you that you have not? You lose something. What does it tell you? It doesn't tell you anything. It's lost. You can't do a lot with things you lost. Okay, I think that's it. Okay.
Just one question. You see, the equality has written the F on those two cups, the F on the left and then the F transposed F on the right. Okay, you found it useful to push it down in the epsilon. It had a sense.
The name, yes.
Is it useful for you?
Yes.
Names.
So no. It's like, I mean, you can write down this like that, and then this is the entangled state corresponding to the linear map. So yes, it's very convenient notation. Yeah.
So that's useful for you.
Yeah. So for lunch, like I suggested before, there is a very good sandwich up there.